Okay, so today I'm going to take you through some energy questions. These are very similar to the questions that were on your energy test. This is going to be on the second day of the review. I'm going to give you a handout with these exact questions on it. And if you look on YouTube, you'll find me solving these same questions. All right, so you need a calculator, something to write with, and I guess a copy of these questions to follow along. Worker pushes a box of books across the floor. With a force of 800 newtons, there's a force of friction of 609 newtons. The box moves 3.5 meters. Find the work done by the worker. Well, for the work done by the worker, the formula is work equals force times distance. If you want the work done by the worker, you only use the force applied by the worker, the 800 newtons. So we're going 800 newtons times 3.5 meters. 800, 3.5 equals 2,800 joules. Work done by friction, same formula, but it's only using the force applied by friction. So, and it's going against the distance traveled, so we call it a negative 609 newtons, 3.5 meters. Negative 609, 3.5 equals negative 2131.5 joules of work. Total work done is easy. You just add up the work done by the worker with the work done by friction. So it's going to be 2,800 joules minus 2131.5, and that gives me total work of 668.5 joules of work. Question number 4, if 195 joules of work is done by an applied force of 50 newtons, calculate the distance traveled. That's just rearranging the work formula to solve for distance. So it's 195 joules divided by 15.6 newtons. And then you just type in 195 divided by 15.6 equals 12.5 meters. A 5.9 kilogram object is raised to a vertical height of 15 meters. Calculate the gravitational potential energy. Gravitational potential energy is Eg equals mgh. And we just go 5.9 kilograms times g, which is 9.81, times height 15 meters. Simple calculation, 5.9, 9.81, and 15 equals 868 joules of energy stored in the object that's 15 meters above the ground. What's the work done to raise an object to this height? Same thing. Because work is equal to, well, whatever type of energy you give the thing. If you sped the thing up, work would be equal to kinetic energy. And if you're lifting something up, then work is equal to the gravitational potential energy that you gave it. Moving on to number 6. It takes 9,000 joules of energy to raise a mass to a height of 60 meters. Find the mass. That's just rearranging the same formula, Eg equals mgh, to solve for mass. So that'll be Eg divided by the other stuff, the g and the h. So we got 9,000 joules. We got 9.81, and we've got a height of 60 meters. So I go 9,000 divided by 9.81 divided by 60, which gives me 15 kilograms, 15.3 kilograms. Number 7, a 6,000 gram ball is moving at a speed of 40 meters per second. Now we're calculating kinetic energy. Formula for kinetic energy, this is on your formula sheet, is 1/2 mv squared. In this case, we're going 1/2 times 6,000. We can't use 6,000. 6,000 grams is 6 kilograms. It's got to be in kilograms. A lot of people mess that up on the test. It costs them. Lots of people also forget to square V. Don't forget to square V. So I go 1/2 times 6 times 40 squared equals 4,800 joules. Next one, a 12 kilogram cannonball has kinetic energy of 2.9 times 10 to the 4, that will be 29,000 joules. What's the speed of the ball? All right, so you can arrange the formula, if you know how to do it, to be root 2 EK over M. But most people probably prefer to just sub into the formula and then figure it out, which is EK equals 1/2 MV squared. All right, so I'm putting in my 29,000 for the energy. My 1/2 is 1/2. We've got 12 kilograms for a mass, and there's my V squared. All right, so 1/2 of 12 is 6, and then I got to divide 6 on the other side. So I'm going to have 29,000 over 6 equals V squared. So 29,000 divided by 6 equals 4,833. You'd think that's what the speed is, but it isn't. That's what V squared equals. V squared equals 483.3. To finish it off, you need the square root of 483.3. So I'm going to hit my square root button, and it gives me a speed of about 70 meters per second. A runner uses 9,367 joules of energy in 5.86 seconds to determine the power. Well, power is equal to energy used, produced, converted over time. So it just gives us these values straight up, 9,367 joules, 5.86 seconds. And as you can see, the units will be joules per second, but more commonly known as watts. 5.86 seconds gives me about 1,600 watts. Number 10, a 4,700 watt generator runs at full power for 3.5 hours. How much energy? That's the power, that's the time, but it's in hours. I'll need that in seconds. To get it into seconds, you're going to go times 60 twice. Times 61 gives you minutes, times 60 twice gives you seconds. So other than that, I'm just going to solve for energy. If I rearrange that, that's going to be power times time. So that's going to be 4,700 watts times 3.5 hours times 60 times 60. That should give me the energy in joules. It should be quite a large number. A joule is not a large amount of energy. So it's, what am I going to say here? 5.9 times 10 to the how many things were there? 1, 2, 3, 4, 5, 6, 7 joules of energy. Could have done it in kilowatt hours, but chose not to in this case. And then we get into these conservation of energy problems. This one's got the, this is the roller coaster question. I think it was on your test. It says a 1,000 kilogram roller coaster goes along this roller coaster and starts at point A at rest, and it goes all the way to these other spots. It says, what's the maximum speed? So the first thing you got to realize with this question is, where is the maximum speed? The maximum speed will be where the kinetic energy is at a maximum and the gravitational energy will be at a minimum. And it's always at its lowest point. So it's going to be at a maximum speed right there at point D. So, and you don't have to go from C. We can go all the way from point A, because we know more stuff about point A. It just starts from rest at point A. So I'm going to say that the total energy at point A is equal to the total energy at point B. At A, I'm going to write it all out. So it's got some gravitational potential and some kinetic energy at A. I'm not writing in spring or elastic energy because there's no springs in this question. Is equal to gravitational potential energy at D plus the kinetic energy at D. Now, one of those terms I can eliminate because it does say that it starts at point A at rest. So that means it's got no kinetic energy to begin with. And that's good for us because because it eliminates a term. It's going to make the math a little bit easier. But we do need this other stuff. We need the gravitational potential energy at A. And it's equal to m times g times the height at A. Over here I've got mg times the height at point D plus 1/2 mv at D squared. All right, that's what we're solving for. This guy right here, the V. If we can manage that, then this is going to work out. So now I've got no choice but to sub in the numbers, I suppose. If you were confident with your math, you might see that there's a mass in each of those three terms, so they can be canceled out. But you don't have to cancel them out because it gave us a mass in this question. It said that the thing is 1,000 kilograms. As usual, G is 9.81, and it starts at a height of 9.5 meters. That's at point A. At point D, still 1,000 kilograms. 9.81 is still 9.81, but now its height is 0.5 meters, plus 1/2, still 1,000 kilograms, times V at D squared. And that's what we have to solve for. So we got to work some of these terms out. I'm going to go 1,000, 9.81, 9.5. So on the left side, I've got 93195. On the right side, I've got 1,000. So 9.81 times 0.5 meters is 4,905. Plus 1/2 times 1,000 is 500. And you've got V squared. Now you've just got to do some of the more complicated algebra you have to do in this course. We've got to move that 4,905 over there and subtract it from 93,195. 93,195. I'm going to do that right now. And it gives me 88,290 when I take 93,195 and minus 4,905 equals 500 times V squared. Next step, divide by the 500. Divide both sides by the 500. So I've got my 88,290. I'm going to divide it by 500, and that gives me 176.58. 176.58 equals V squared. That's not the speed. That's way too fast for a roller coaster. We still have to take the square root to find the answer. So I still have my 176.58 in my calculator. Just hit the square root button, and it gives you a maximum speed of this roller coaster of 13 meters per second. That is one of the more complex calculations you'll have to do on this exam. There should be a question like it on your final exam. Let's try another one like the roller coaster question, except instead of gravitational and kinetic, we're going to deal with kinetic energy and elastic potential energy. A block of mass 2.5 kilograms flies towards that spring at 3.0 meters per second. How much will it compress the spring before it comes to rest? All right, so there's no height change, so I'm not going to put any gravitational potential energy. I'm going to say total energy initial equals total energy final. To begin with, well, I'll write all the things out. So we've got kinetic energy in this question. So initial kinetic energy, initial spring energy equals our final kinetic energy plus our final spring energy. Good news is, before it hits the spring, you know, when it's right here, it's not touching the spring, so there is no spring energy. You only start to store energy in a spring when you make contact and start to compress or stretch a spring. And when it's just moving, it's got no spring energy. Also says that how far will it compress the spring before coming to rest. So that means when it hits the spring and compresses it, well, it's going to reach a maximum compression when it comes to rest. So that means there's no final kinetic energy. That makes the math in this one a lot easier. So all I've got is EK initial equals spring energy final. Kinetic energy, same formula as always, 1/2 mv squared. I'll say initial for the speed. is equal to, the formula for spring or elastic potential energy is 1/2 kx squared, where k is the spring constant or the stiffness of the spring, and x is the amount that the spring is compressed. All right, so I might run out of room here. I'm going to try and sub in the values. So that's going to be 1/2. Oh, I got to go up a bit. I need to see the mass. 2.5 and 3. So I got 1/2, 2.5, 3 meters per second, and that's squared, equals 1/2. I got to look back at the question again and find, well, how stiff is that spring? Does it tell me? 360 newtons per meter is the stiffness of the spring. That's always the unit for the spring constant or the stiffness of the spring. 360 newtons per meter. Bracket, bracket, and then I've got x squared. That's the only unknown. So on the right side of the equation, I've got 1/2 times 2.5 times 3 squared equals 11.25. I'm going to continue up here. 11.25 equals, on the other side, I got 1/2 of 360, and that gives me 180 times x squared. Divide 11.25 by 180. It's going to give you a real small number, 0.0625 equals x squared. That's not the answer to the question. Just like before, we need a square root. And we get that x equals 0.25 meters. That's how much the spring compresses. Doesn't seem like much, but that's 25 centimeters, you know, like it's like a quarter of a meter stick. So that's a lot for a spring to compress, I think. Sarah uses an inclined plane to push a container into a truck. The back of the truck is that high, and the container, the mass is 125 kilograms. Determine the gravitational energy of the container in the truck. Well, that's simple. Gravitational energy, Eg equals mgh, equals 125, 9.81, and 1.95 meters. 125, 9.81, and 1.95 meters. And that gives me this gravitational potential of 2391 joules. All right, there's part A done. What about part B? All right, part B says, well, she had to put in this much energy due to friction and other energy losses. So what's the percent efficiency of the ramp? All right, if you're looking for the efficiency of an energy transfer, you just divide the energy that you got out of your work divided by the energy that you had to put in times 100, all right? In this case, what did she want to do? She wanted to give the thing gravitational energy. So the energy, the useful energy that she got out is her 2391 joules, but due to friction, she had to actually push with 3519 joules. We're going to multiply by 100, and that gives us a percent efficiency of 68%. One more question today, I think. That should be it. One of these crazy temperature questions. I need to go back up just a bit. There we go. How much energy do we need to take the temperature of 2.5 kilograms of water from -20 to 57? All right. You might remember one day in class, I went with temperature. And time, and said when you heat something up from freezing, it gets to a plateau when you have to melt it. And that once it's all melted, then it'll start to increase in temperature again. And there's some heat where you increase the temperature initially from -20 to 0. Then you got to use some energy to actually turn the ice into a liquid or the solid into a liquid. And then we can raise the temperature again with some heat. So there's 3 heat calculations we have to add up here. And the formulas, at least for, first let's go from -20 to 0. And that's just going to use EH equals MC delta temperature. All right, and that's 2.5 kilograms. I believe the heat capacity of ice is 2100 joules per kilogram degree Celsius. And the change in temperature, negative 20 to 0, it goes up 20 degrees, so positive 20 degrees. 2.5 times 2100 times 20 gives me 105,000 joules of energy. That just gets me to here. That's what I've done so far. I've gone from there to there. So don't stop there. We also need to, the next thing we have to calculate is this. And that's what we call latent heat, this hidden heat that's required to take this thing a little bit further. So what am I going to title this one? I'm going to say melt. What's it going to take to melt this thing? All right, and that formula is EH equals the latent heat of fusion times the mass. The latent heat of fusion for melting ice is 2.3 million joules per kilogram, which is 2.3 times 10 to the 6 joules per kilogram times 2.5 kilograms. So just to melt that hunk of ice, 2.5 and 2.3 XP6, it's going to take 575,000 joules of energy. Last section. Oh, and there's the lunch bell. Last section, you just use EH equals MC delta T again. Except now the heat capacity, C, is 4,200 joules per kilogram degree Celsius. You'll have to add those heats up, the initial, the middle, and whatever you get for the final, and then you get a total energy. That's it for today.